right? So, I mean, we're making some progress. So, but now we're going to get into real statistics. We're going to get into material that you'll use, things that you'll do and use, statistical analyses that you'll collect data and actually apply, and so on and so forth. So we're really, I mean, we kind of got started with that when we started talking last week about confidence intervals, right? Because you see that in abstract. When they give you an average for a numerical variable, you almost inevitably see, if they tell you that in their study, the average of this measurement was 100, they'll almost inevitably tell you what the confidence interval that goes with that is, right? So I'm going to go over that a little bit again. But we made a critical assumption when we've been talking about confidence interval up to now. And that critical assumption is that we know what the population standard deviation is. We know what sigma is, right? That's usually not true. We usually don't know any more of what sigma is than we know what the mean is of the population. That's the whole reason why we sample. However, we know that when we take repeated samples from a population, the bigger the sample size is, the more confident we are that the mean of our sample estimates the mean of the population. It's the whole reason for doing it. The whole reason for taking a sample is to have a educated guess about what the mean of the population is, at least for a numerical variable, and for proportion, which is point estimate that we use for a binomial variable, for something that has two values. So, and we see that with each of those point estimates, whether it's a proportion or whether it's a mean, that we can generate based on the variability in the population, we can generate a pretty accurate picture of what our confidence interval is, what this range of numbers is that I can say with a certain level of, with a known level of confidence, like say 95% confidence, that the true proportion or the true mean is between those two numbers, right? So that gives us a lot better picture of what the true population mean is than just throwing, throwing out a number like the average blood pressure in this population is 82. Rather than just throwing out that number, we get a much better picture of what we really know about the average blood pressure in that population. If we can also say the average blood pressure is 82 with a 95% confidence interval of 80 to 84, we get a picture now where we might be with that. How certainly, to what certainty we know the true population mean. All of that depends on the fact that we understand the variability in the population. If there's a lot of variability in the population, like the blood pressures went from 60 to 190, and there's an enormous amount of variability, then our confidence interval is going to wind up being wider because our standard error is going to be a big number. Standard deviation of all the sample means it's going to be a bigger number, and so on and so forth. So that variability is going to make our confidence interval wider. If the population values are not very variable, in other words, instead of being that variable, maybe they range from 70 to 90, right? So they're much more compact. Well, that gives us a lot more certainty about what the distribution, the normal distribution, looks like, and tells us and helps us to get our 95% confidence interval to be narrower than it would have been if there were a lot of variability. But all of that is based on the fact that we're assuming to begin with a normal distribution, and that we're assuming that we know accurately, completely, what the true standard deviation of that population is. Even though we don't know what the mean is, we know what the standard deviation of the population is. Since we would have to measure everybody in the population to know what the standard deviation is of the population sigma, it's unlikely we're ever going to know that. Just like unlikely we're ever going to know the true mean, because we're not going to measure everybody. That's why we take a sample. So the issue there is, well, if I don't know what the population standard deviation is, which is 99.9% of the time you're going to be using statistical tests, you don't know anything. You don't really know that about the population. You don't know any of the parameters completely about the population. What are we going to use to determine what the standard deviation of the population actually is. You got a guess on that? What do you think we'd use? Well, we use the sample to estimate the population mean, right? So how about the sample? Right, we just take the sample values that we took itself, and the variability in the sample could probably be the same as the variability in the population as well. So just like we use the sample to estimate the population mean, we can use the standard deviation of the sample that we took to estimate the population standard deviation. So instead of using sigma, we're going to use the standard deviation of the sample. Well, problem with that is we went through this whole thing about how to calculate confidence intervals with the assumption that we know what the population standard deviation is. Now we don't. Now we have to estimate it. We have to take it from a sample. So all of a sudden, we're going to be less certain about our confidence interval because we don't know what the population standard deviation is. We have to estimate it from our sample, right? Just like our sample's not going to come out with exactly the mean of the population, but it'd be close. Just like that, our sample standard deviation is not going to be exactly what the population standard deviation is. So we have to make up for that uncertainty, the fact that we don't really know what sigma is, and we have to estimate it from our sample. So just from the perspective of a confidence interval, what do you think that's going to do to our 95% confidence interval? If now we've injected an extra level of uncertainty, is it going to make it wider or narrower? I love that you're here because now I could just pin this on. You're the only one in the room. Yeah, you can't escape. Wider, exactly. In other words, we have to make that confidence interval wider, so to make up for that extra level of uncertainty that we've introduced by not actually knowing what the population sigma is. Great. So that's what we're going to do today. We're going to try to understand how to estimate that, how to make up for that extra level of uncertainty. Okay, and that is going to be something called a t-distribution. You probably have heard somewhere in the back of your heads or previous statistics course or just in reading a study or something like that, you've probably heard about the t-score or t-distribution and the student's t-test, right? You probably heard that somewhere. So today we're going to start to introduce that. We're going to introduce it slowly. So we're going to talk about the t-distribution, how we're going to use it, and how it's going to amend our confidence interval, because of the extra level of uncertainty, how it's going to affect our confidence interval. And then next week, we're going to get into something called hypothesis testing, where we're going to, for the first time, really take two populations, compare the two populations, and try to prove with a certain level of certainty that there's a difference in the mean of the two populations, right? So that's, for instance, if we wanted to find out if a placebo or a drug lowers blood pressure, has more of an effect on there's a difference between a placebo and a drug in terms of lowering blood pressure. That's the kind of test that we would use. We're comparing the means of two groups in a clinical study like that, or the means of two groups in a population study, for instance, whether Frenchmen drink more wine than Italians do. We know they drink more than Americans, but the question is, do they drink more wine than Italians do? That's right. So we have mechanism. Now we have a mechanism to do that. We can use it for means and we can use it for proportions, but it's called a t-test. And we're gonna just start to introduce it today, so so that we don't get too confused by this whole thing. And then next week we'll really start to apply it. So we're going to have a little bit of review. So today's work folder, week 7. I think it's week 7. I'm not sure exactly how to classify it. There's some reading that you can do in the textbook. I think in the older version, if you're using version 3, that I think it might be chapter 4, but in version 4 I think it's 5.1 through 5.3. Okay, but you might check that. But as we work through this, you'll see what we're covering now and where that is in the textbook in chapter 4 and 5, and then 6 as we progress forward. Okay, so I'm going to start with some material that we're going to work on now. Actually, I have this already I have this already on my desktop, so I'm going to open it from there, but you can open this material from here if you want to. Also, you may notice that I've taken a video from a previous semester and I've broken it up into a sequence of shorter videos so that later on, if you want, if you're struggling with, what I'm doing now, continuously as I'm working through it, and you want to go back over some part of it or something like that, you can use those from a previous semester. Okay. Then in addition to that, you also have, I gave you a couple of tables that we're going to be using, the Ztable, which we're familiar with, and a new table called the T-table. The names in front of that, Agresti, Franklin, Agresti, they're just the names of the textbook that they happen to come out of. The identical text, the identical charts are in the back of your textbook as well. Okay, and there's also then after that, there's a PowerPoint and a lecture recording on hypothesis, on just introducing hypothesis testing, just breaking into this idea of comparing groups and so on and so forth. This is a little bit more theoretical and intangible, but I'm leaving it up here so when we're done here, you can watch this on your own today, or you can, so anytime before next session, it'd be a good idea just to watch this lecture video, kind of prepare for the next step we're going to take. Don't worry about it if you find it a little bit difficult to understand or to interpret. We'll be breaking it down into kind of simpler blocks next week as well. Okay, so I'm going to leave that on there so you guys can watch that after we're done. I'm referring to you as you guys now because, Okay, good. If you're listening online, it's because I have one student here that I'm mostly directing this to, even though I'm making believe I'm talking to a million students. But I think we got at least one or two other students online now that have tuned in since I started. Okay, so let me get into these exercises. Okay, let's start with this one. Okay, and we're going to start off with some repetition from last week. Okay, population of the mean of a population is known to be 160. Notice mu, so we know it's population, that's a parameter, okay? And the standard deviation of the population is known to be 18 sigma. Again, we know that's the standard deviation of the population. What would be the probability that a single observation selected at random from this population would have a value less than 142? Well, I'm going to grab a piece of paper or an imaginary piece of paper, if I can find it here. Where'd it go? Oh, I'll use this. Can't find the whiteboard on here. Oh, I don't want to use that. I'll use the text thing. Don't need that one. Let me get a blank. Okay, good. I'll bring that down here so we can see it. And I'll get hold of a pen to write with. And hopefully my tablet is working and I'll be able to write on this. Okay, so the mean, this is a normal distribution, presumably a normal distribution. The mean is 160, and the standard deviation is equal to 18. What would be the probability of single observation in a random population with a value of 142? Well, 142, probably around here somewhere. So less than 142. So we're interested in the probability that the individual that we select from this population is in this area of the distribution, less than 142. Okay, we can look at this two ways. We can look at this as the proportion of the population that is under 142, number of people, or we can look at it as a probability that we would select a person that is in this group, which is the same thing as the proportionality of the population that's below this. Okay, so let's give this a try. So how do we know what percentage of this population is in this area? Well, we know that we can use the Z-table to calculate that. Okay, so in order to figure that out, I need to know what the z-score for 142 is. How many standard deviations away from the mean 142 is. So we can just kind of do it in our heads, or we can actually use this formula. X is the value that we're interested in minus the mean over the standard deviation. In this case, 142 minus 160 over 18, which is equal to 18 over 18, which is equal to 1. So now, as we mentioned before, the empirical formula, the empirical rule tells us that that one standard deviation below the mean to one standard deviation above the mean represents 68, approximately 68% of the population. So that would mean, since we know the normal distribution is symmetrical, that would mean that this part below the mean would be 34%, this part above the mean would be 34%. And we know that from the mean down or the mean up, it's 50%. So if this is 34, what we're left with here is about 16%. We're going to become more accurate as we move on through these examples. And in order to be more accurate, we're going to probably have to at some point ditch the empirical rule and actually go to the tables to calculate this. What's the probability a single observation has a value greater than 166? Well, now that's a little bit of a problem for us now, right? So here's 166. Oh, by the way, I noticed that this was not 1, that was minus 142 minus 160 is minus 18 over 18. So that's a minus 1. It's one standard deviation below the mean. So now I'm going to take a look at 166. What's the probability a single observation has a value greater than 166? So Z is going to be equal to 166 minus 160 over 18. Okay, and that's going to be 6 over 18. So that's going to be equal to 0.333. It's going to be a repeating number. That's going to be a positive number, right? Now it's a positive number because it's on the right side of the mean in this population. Okay, so we're going to take a look at this. It's a positive number. So now we also notice that it's asking for me for the area above 166. In other words, what's the probability that we would randomly select someone that has a value greater than 166? So now we know that when we go to the empirical rule is not going to help us here because it's not an integer value of the z-score. So we're going to wind up going to the z-table. But we also know that when we go to the z-table, it's not going to help me in terms, at least not directly, in terms of the area above this value, which is what we're interested in. It's going to give me the area from there down. In other words, the entire portion of this distribution that's below 166. Okay, let's give that a try, see what we wind up with. Okay, let me go back here and get the z-table. Okay, so I'm going to scroll this up here a little bit, get it out of all my scribbles. And so we're looking for a 0.3, and we know that we use the z-score. This is going to be our first two digits. Is going to be 0.3, and then our fourth digit is going to be found by going across these columns. So 0.033. This is 0.30, 1, 2, 3. So it's going to be 62.6293. Okay. So this area is going to be, oops, I'm sorry. This area from there down is going to be 6, 9, and I've already forgotten it. Remember what it was? 629. Thank you, 6293. Great, thank you. Actually, I could have just said 63, but at 63, it's about 63%. So this area is about 63%, right? So since the entire distribution, entire population represents 100%, that leaves us 37% of the population is above 166. Similarly, the chances of randomly selecting someone from this population and having a value above 166 is 37%, 0.37, right? So if I want to do it a little bit more accurately, I could take our actual value from the table, 0.6293, and actually subtract it from 1. That's going to be 7, 0, 9, it's going to be 7, and 3. 0.3703. Yeah, that looks right. Right. So that is the proportion that's above. And of course, almost inevitably, if I annoy you with this, the next thing I ask you, what's the probability that a single observation is value between 142 and 166? Okay, well, we just did everything we needed to know what that is, right? So we know that this area here, this area down here is 16%. I could look it up more accurately if I want to. And this area up here is 37%. So this area is 16%. This area is 37%. I'm going to just do it quickly rather than spend a lot of time on it. So the area between 142 and 166, which is what it's looking for, right? That area is going to be equal to 100% or 1.0000 minus this area and this area. So it's going to be, I'm going to just add them together roughly. 37 and 16 is 53%, right? So if that's 53%, if these two add up to 53%, that leaves 47% between these two values, the value that we're looking for. Okay? Good. Okay. Let me erase that. Okay, so let's see what it looks like on our next example looks like. Oops, I didn't turn off my pen. Okay, so now take the next step here. In this case, we don't know what the population mean is. We're dealing with a random sample of size 36. Since we're dealing with a sample and I'm telling you what the mean is, I'm going to use X bar instead of mu to describe that mean. That's the mean of our sample. We're hoping that it approximates the mean of the population, but that's what we know about it so far. Assume that the population normally distributed with a standard deviation sigma is equal to 18. Pretty similar to before, except now we're guessing at the mean, right? We think, when I say guessing, I don't mean a real guess. We're taking an educated guess of what the mean is based on our sample, right? Our average of our sample. But for some reason, we have information that tells us what the standard deviation of the population is for this particular measurement. You know, it isn't impossible that you might be in this situation. It could be that someone did an enormous study last year in the same population, measuring the same thing, and now you want to look to see if the mean has changed, and you might be tempted to say, well, even though we don't know what the mean is for the new year or new group, we're going to make the assumption that the standard deviation of the population is the same as the one that we measured before, right? So it is possible you might, but not likely. Okay, so that one caveat there. So let's see what we can do with this. So what we're interested in, when we have information like this, what we're interested in knowing is we're interested in knowing if this is the mean of our sample, how certain can I be that I'm close to the mean of the actual population? Okay, so in other words, what is our confidence interval for this sample mean? How confident are we that this sample mean really captures the population mean? Okay, so let's get a piece of paper again and see what we can do with this. Okay, so let's see what we know about this. We know that the standard, first of all, we know that the mean X bar for our sample is 165. And we know that the standard deviation for the population is 36. Oh, excuse me, is 18. And we know our sample size, right? Because we determined that right at the beginning. So we're going to sample 36 people. Okay, so now if I want to calculate a confidence interval for my mean for my population, I'd be using this formula: X bar plus or minus 1.96 times the standard error. Okay, so why am I using that formula? Why am I using 1.96? Because 1.96 represents the number of standard deviations away from the mean that would represent 95% of the possible outcomes. That leaves 2.5% at this end and 2.5% at this end, right? Well, you know, if we're talking about -2 to +2 standard deviations being 95% when I use the empirical rule, well, why am I not using 2 here? The reason why I'm not using 2 is because the empirical rule is an estimate. To really get 2.5% in this tail and 2.5% in this tail, I have to be minus 1.96 standard deviations to the left of the mean and plus 1.96 standard deviations to the right of the mean. You might recall that we confirmed that by looking at the Ztable and determining what area that I needed to have 2.5% here. Well, let's see, what z-score does that require? In order to get 2.5% in that left tail, right, I would need a z-score of 1.96, right? And that's where that came from. Okay, so that's great. So I know that. So now let's figure out how we're going to calculate our confidence interval. Okay, so X bar is 165 plus or minus for a 95% confidence interval. 1.96 times our standard error. Our standard error is the variability. In other words, we have an original population, right, which has a mean of that we don't know. We don't know it yet, and a standard deviation of 18, right? So now that's our original population, but our standard error is the standard deviation for repeated samples of size 36, for the means of repeated samples of size 36. That's inevitably going to be narrower because each one of these means is going to be closer to the population mean, just by virtue of the fact that it's a sample of a large number of people from that population average, random sample average, right? So this standard deviation, the standard deviation of its new sample mean, is equal to the standard deviation of the population over the square root of the sample size. Bigger the sample size becomes, the smaller the standard deviation of the individual sample means is going to be. Okay, so that's going to be equal to 18 over the square root of the sample size, 36, which is 6. So that's equal to 3 in this case, right? Had it been a larger sample size, this number would have been smaller because n would have been larger, and it's in the denominator, it's in the bottom. Okay, so I know that the standard deviation of repeated samples of size 36 is going to have a standard deviation of 3. How do I know that? I know it because I know the variability in the population exactly. I know exactly what standard deviation. I'm not guessing like I am with the mean. I know what it is. I call it sigma because I know what it is. So I can apply this rule. So in order to not confuse standard deviation when we use it here, standard deviation when we use it there, when I'm talking about the sample means, we're going to call it standard error. Okay, so, and the standard error is equal to sigma over the square root of the sample size in this case. Okay, and that's equal, we just calculated it, that's equal to 3. So our confidence interval is going to be 165 plus or minus 196 times 3. Okay, so I'm going to round this off and just say 6, right? So our confidence interval is going to be Occasionally, I will actually calculate it out just to make sure that you know how to do it, right? But for right now, I'm just going to say 6. So I'm going to say it's 159 to 171. We're 95% sure that the true population mean is between these two numbers. This is the mean that we got from our sample, but this range, we're saying that we're 95% certain that it would be within these two numbers. If we repeat this study 100 times, 95 out of 100 times, we will get a range which captures the true population mean. But 5 times out of 100, we might not, right? 20 times, one time out of 20, it's likely that we might not. 19 times out of 20, it's likely that we did capture the population mean. So that's why we're doing this. That's really the whole impetus behind doing this, is so that we can have another way of describing what the population mean is that gives us some feedback on what level of certainty that we know it with. Okay, so let's take a look at the next question, which is going to ask us, actually, I don't even have to bother, I don't think. I think the next question is, what about if the confidence, what if you want to know it with more certainty? That you want to see a range that's less likely to miss the true mean. You want to be 99% confident that you've actually captured the true mean between those two numbers. But if you want to be more certain, you have to have a wider interval, right? If you're willing to be less certain, you can make the interval narrower, because when you make it narrower, it makes it less likely, makes it a little bit more likely that you'll miss the population mean. So if we want to be 99% certain, then we would have to have a distribution where this tail, instead of having 2.5% on each end, is only going to have 0.5% on each end. So we have 99% of the possible sample outcomes, possible means in between those two numbers. Okay, so in that case, instead of using X bar plus or minus 1.96 times the standard error, we would use X bar plus or minus 2.58 instead. And where's the 2.58 come from? It comes from the Ztable, the Z value that represents 0.5% in the tail at the top and the bottom of the distribution, plus or minus 2.58. So 165 plus or minus 2.58 times our standard error, which is equal to 3. So I'll actually calculate it out this time. Whoops. Let me clear out memory. Okay, so 2.58 times 3 is equal to 7.74. I'm going to put that into memory. And then I'm going to take 165 in this problem minus our margin of error. Remember, when we actually calculate that, that's called the margin of error, is equal to 157.26 157.26 to okay, 165 plus our margin of error is 172.74. Okay, so we're 99% certain our true population mean is going to be between these two numbers. Well, what about if I want to be 90% certain? If I'm willing to be a little less certain with my confidence interval? Well, in that case, you can make your confidence interval narrower, because you're willing to take a little bit more risk that that your mean is outside of that range. In that case, we would use a Z value of X bar. And the reason why I say Z is because frequently you'll see this indicated as Z for whatever certainty that you want, whatever level of uncertainty, alpha is equal to 10, for instance, 0.1, 10%, right, would be 90%. Okay, so 90% uncertainty. So that number times standard error. So that number is going to be X bar plus or minus 1.64 times the standard error. Okay, that would be our 90% confidence interval. Okay, I'm not going to bother to do that one. Just a little bit more math. Eek. I guess I don't have my pointer on. Good. Okay. Okay, let's see where we go from there. Okay. So now, let's see. Okay, good. I think we got all of that, right? Okay, this 3A is basically the same thing. Okay, I'm going to skip over to 3B, which now introduces a little bit of a change. A random sample of size 15 has a mean of 150. The standard deviation of the sample is 30. Well, something changed here, right? Something important changed. And that is that instead of knowing the standard deviation of the population, sigma, we now know that's unknown now, just like the mean is unknown, right? We now know instead X bar and the standard deviation of the sample itself. In other words, the standard deviation or variability of those 15 people that were in that survey, right? So our mean is 150 and our standard deviation is equal to 30. Well, what do we know about taking samples from a normal population? What we know is that the mean of our sample approximates the population mean. We also know that the variability of our sample, standard deviation, approximates the population standard deviation, right? So we can take advantage of that and say to ourselves, well, you know, I don't know what sigma is, but I'm going to assume that sigma is equal to 30, that sigma is equal to 30, just like the sample that I took. Okay, now, the thing is that we really don't know that for sure. We know that, you know, if we have a decent sized sample, we should be pretty close approximation. If we have a small sample, we're less certain. If we have a big sample, we're more certain that it's pretty close to the population standard deviation. If we have a really big sample, then we're really a lot more certain that we're close to the true population standard deviation. So now, when I'm looking for my margin of error, how much error am I into, you know, what range do I have to have my confidence interval? I know I have to make it wider now for the same situation, for that be 95% certain, because I've introduced extra uncertainty by using the standard deviation of the sample instead of using sigma, which I don't know now. Okay, so let's calculate the standard error for a sample of size 15. So normally our standard error would be equal to sigma over the square root of n. Well, now we don't have sigma. We have to instead use standard error is equal to the standard deviation of the sample over the square root of the sample size. Okay, in this case, that's going to be 30 over the square root of the sample size, which is 15, square root of 15. Okay, a little bit of a weird number, but we'll get to that in a second. Okay, so actually, you know what I'm going to do? I'm going to make this 16, just to make it simple. Okay, make it 16. So that's going to be 30 over, well, it doesn't make it much more simple, but okay, makes it something. So is equal to 7.5, right? Just simplify things a little bit. Okay, do a little bit less math. Okay, so our margin of error is our standard error is 7.5. Now, what's our margin of error? Our margin of error is this, plus or minus. Well, I'm going to put some number in here times 7.5. Well, now, since I'm assuming that this is the population standard deviation, when it may not be, I have to make up for that extra level of uncertainty. So instead of putting in the value from the z-score for 95% certainty, in other words, 5% chance of being wrong, alpha is equal to 0.05. Uh, uh, Remember we talked, at some point we talked about alpha errors and beta errors. Alpha error or type 1 error is the probability that you would be wrong if you that you would be getting a value that's so extreme it's outside of the 95% of the normal population. So, our z-score, which would have been 1.96, we have to adjust that, right? Because we have to make that number bigger because we're multiplying it by a number we're not so sure of. So we need our confidence interval to be wider, right? To make up for the extra level of uncertainty. But now, am I going to wind up with a single number for the z value? Or for what I'm going to place in front instead of the z value? Well, the problem now is that, yeah, I got to make my confidence interval wider. But if my sample is really big, it's only a little bit of uncertainty. So I only got to make a little wider. But if my sample is small, like this sample is only 15, if my sample is small, well, I have to make it wider because I'm even more wide because I have a greater level of uncertainty. If my sample size is 5, I got to make it much wider, right? So I have to determine, how do I know how wide I should make it? Well, in fact, we have a version of the t-distribution, which is called the t-distribution. And the t-distribution has it's a distribution that is specific to every sample size. If the sample size is 100, you got one. If sample size is 50, you got another. Sample size is 25, you got another amount of variability. So instead of having one z-table as we do, we now have many t-tables. T-table and imaginary t-table for every possible value that you could have for the sample size. Well, that's going to be kind of cumbersome. We'd have a textbook full of t-tables. So instead, what we have instead is we have the t-value that you need to substitute for that 1.96 based on your sample size. We have a single table that gives you the important values for t, not the entire table, like we use for the z-table to calculate all different possible areas, but only for the areas that we're really critically interested in, 95%, 99%, 90%. Let's open that table up. Okay, here's this version of the t-table. Well, if you look at this version of the t-table, let me get rid of all this stuff. If you look at this version of the t-table, what is it telling you? It's telling you that you can have a confidence level, a confidence interval of 80%, 90%, 95, 98, 99, 99.8. Any of these, so let's start with 95. That's the one we will use most frequently. The value that you're going to use instead of 1.96 is going to be a larger number than 1.96 because you've introduced some uncertainty, right? So what is that value going to be? Well, if your sample size is, I'm going to ignore this DF thing over here for a second and just make believe this is sample size. It's not really. But let's say your sample size is 10. Then instead of 1.96, we would use 2.228. Okay, so that's going to give us a bigger margin of error and make our confidence interval wider. So now let me see what happens if my sample size is 25. It's going to be 2.06. It's still bigger than 1.96, but it's still bigger, but it's not quite as big as it was when the sample size was smaller. Well, let's see what happens as my sample size gets bigger and bigger. The value that I use instead of 1.96 gets progressively closer to what? 1.96. And 1.96 is the value you would use when you reach an infinite sample size. No such thing as an infinite sample size. What is that really? That means when you know the whole population, right? That's when you know sigma, you use 1.96. That's how we use this. So what are we going to use in this example where we had a sample size of 15? Well, this number here is not the sample size exactly. It's the degrees of freedom. By degrees of freedom, when we talk about variability, if I just gave you one number, 10, right? What do you know about the variability if I just give you one number? You don't know anything. You don't know if the next number is going to be 100, 1,000, or 9, right? You don't know anything about the variability. So you really only start to know something about the variability when you have more than one value. When I say, oh, I sample one person, he's 10. Sample the second person, he's 20. Oh, well, now I know a little bit about the variability. If I keep adding people, I know more and more and more about the variability. So instead of looking at this in terms of like sample, we wouldn't want to deal with a sample size of 1 because it's meaningless in terms of variability. We're going to start with 1 representing a sample size of 2. In other words, the degrees of freedom is the sample size minus 1. So if we have a sample size of 15, we have 14 degrees of freedom. Okay, so 14 degrees of freedom, a 95% confidence interval, the value I should be using instead of the Z value of 1.96 is the T value for 95%, 2.145. And if I wanted to be 99% confident, I would be using 2.977. In other words, wider than 2.145. Okay, so let's just start with 2.145. Okay, so the 95%, okay, so the margin of error is equal to 2.145, right? That's T for a sample size of, that's for a sample size equal 15, right? Times our standard error. T is equal to alpha, alpha is equal to 5%, 5% chance of being wrong. Okay. Sometimes you'll see it as alpha over 2 is equal to 2.5%, and so on and so forth. Don't worry about that. Yeah, as long as you understand that we're substituting this for 1.96 so that we make up for the uncertainty of using a sample for our standard deviation in the population instead of the actual sigma. So 2.5 times my standard error, and my standard error is going to be equal to our standard deviation 30 divided by the square root of the sample size, square root of 15. So what is that equal to? It's equal to 30 did I say it was going to change? I said I was going to change it. 16. 30 over 4 is equal to 7.5. So our 95% confidence interval for a mean of 150 is 150 plus or minus 2.145, I think I see it, there it is, times our standard error, which is 7.5. Had we known what sigma was, then this would have been 1.96. Had the sample size been bigger, then this would have been closer to 1.96, right? All of those things are true. So our 95% confidence interval is going to be, and I'm going to take, now that I'm going to actually calculate it, I'm going to go back to the original values. Oh, let me do this first. I'm going to do the original values. Equals 30 over the square root of 15. Okay, let me clear out memory. Okay, so square root of 15. Okay, 30, I'm going to do it in one step. 30 divided by, will let me do this? No, I don't think so. 30 divided by square root of 15. That looks like about 4 into 30. Less than 4. That looks right. I think that might be right. I tried to save a step there. I'm hoping that that's right. 7 point. So I'm gonna put that into memory. Oh, actually, hang on a second. Yes, I'm going to put that's my standard error. Now I have to multiply that by 2.145. 2.145. And our margin of error now is 16.6. You okay with that? Do you agree with that? Looks right? Okay, I think it's right. Okay, so that's our margin of error. I'm going to put that into memory. See if it's in there. Yep, it's in there now. I'm going to clear that out. I'm going to say 150 minus our margin of error is going to be equal to 133.4. Oops, 133.42. Okay, 150 plus our margin of error, 166.6. Okay, so that's our confidence interval. What would it have been if we knew what sigma was? This would have been, the only thing would have changed, this would have been 1.96. What if the sample size was larger? If sample size was larger, the n here, the square root of n would be a bigger number, divided into 30 would make it a smaller number. The standard error would be smaller, so we'd wind up with a narrower confidence interval. What if we want it to be 99% certain? Well, when we knew what sigma was, that meant instead of using 1.96, we would use 2.58. In this case, what we would do for 99% certainty is we go back to our table, and 99% for 14 degrees of freedom would be 2.977 is the number that we would use here instead of 2.145. Right, quite a difference, right? Okay, and the confidence interval will be different as a consequence of this. Okay. I'm going to clear this out. Okay. I don't like that example because it goes back, it takes us a step back. Okay, now this next problem. I'm going to change this just a little bit. What is the 95%? Okay, what's 95% confidence interval? Average weight into count counting. What would be the 99% confidence interval if our sample size were 100? Okay. Now the mean, the mean that we got was, I'm going to say the mean is X bar is equal to. I'm going to change this a bit. Say the mean weight of men in our sample of DeKalb County men is 180 pounds. Okay, so the mean weight in our sample, in other words, X bar is 180 pounds. What would be the confidence interval if our sample size was 100? Okay, now remember, our sample size is going to be 100. Okay, what's the 95% confidence interval for our sample size of 25? And now I'm going to ask you, and then we'll see what the, well, what do we think is going to happen here in these two? It's going to, it looks, since our sample size is 100, right? Instead of using Z as 1.96, we would use another value of the value for T for 99 degrees of freedom, which is going to be a little bit more than 1.96. So if it's a little bit more than 1.96, we're going to wind up with a slightly wider confidence interval. But now what if the sample size were only 25? Well, now, again, I would not use, since it's a sample, I would not use the z-score of 1.96. I would use the t-value for 24 degrees of freedom, which is going to be a bigger number than the t-value for a sample size of 100. So this is going to be wider than it would have been if it were 1.96, and wider than it would be for when we did it for a sample size of 100. Okay, so I am going to leave that up to you to do. Okay, I think why don't you give that a try? I'm gonna run out for a moment, take a break. Why don't you give that a try, see if you have any success with that. Okay, those of you guys that are online, give that a try also. Okay, I'm gonna mute. Here. Okay, guys. So hopefully you taking the opportunity to give this a try on your own. So let's actually go ahead and solve this. So, pencil. Okay, so our mean of our sample is 180. Our sample size initially is 100. And our standard deviation for, did I have it there? Where is it? Let me drop this down a little bit. What did I say? Standard deviation was 30. Our standard deviation is equal to 30. Okay, and let me get this back. And our standard deviation of our sample is equal to 30. So if we wanted to calculate our confidence interval for our sample mean, it's going to be X bar plus or minus, and since it's a sample, now I'm going to dip into a little bit of a controversy here. You may remember that when we look at the t-table, that the closer that we got to the entire population, the closer we got to a t-score or to the t-score being the same as the z-value, which was not 1.96. So a lot of, when you do some initial calculations for confidence interval, some initial look at your data and so on and so forth, a lot of researchers will say to themselves, you know, if I have a large sample size, it's getting so close to 1.96, I'm not going to bother looking at the t-table. I'm just going to use the z-table instead. Is that completely accurate? No, it's not, because anytime we have less than the entire population, in terms of like what the standard deviation of the population is, anytime we have less than sigma, less certainty than having sigma, we have a little less certainty in what our confidence interval is. So technically, anytime you're working with standard deviation derived from a sample instead of from the actual population, then you're making a compromise by using 1.96. But because we're human, we say to ourselves, gee, if a sample size of 100, it's so close, 1.98 compared to 1.96, I may just use that instead. So you may say to yourself, if you have a large sample size, I'll just skip looking up the t-value and instead use 1.96. What do you define as a large sample size? You can read 10 textbooks and get 10 different answers on what they consider a large sample size. Some textbooks will say anything over 30 is a large sample size. So 29 degrees of freedom would be 2.04, it looks like, right? So that's pretty close, right? But maybe you want to make 50 a large sample size because it's close, it's 2.09. Maybe 100, you know, so we get into like, you know, a debate over what's a large sample then as well. So you can either choose to say, it's 100, I'm going to stick with, for instance, on an exam, chances are if it's a sample size of 100, when you put down the answers, I probably would make enough, you know, I always put in a range that's an acceptable answer. My guess is that most of the time, if I do something like that, if it's a sample size of 100, the range is probably going to be wide enough that if you use 1.96 instead of 1.98, you'll still get it marked correctly, right? So you could probably get away with that with sample size 100. But technically, you should be using the t-score no matter what the size is. Now, what about SPSS? What does SPSS do? SPSS can calculate confidence intervals, and we'll play around with that a bit next week. SPSS can calculate confidence intervals. What does SPSS do with this? Well, SPSS has every t-table built into it. Actually has a formula to calculate t-values built into it. It always uses the t. It doesn't care if the sample size is 150,000 people. It's gonna calculate a t-value, and it might be 1.9600001, but it's still gonna use the t-value instead of the 1.96 when it's evaluating a sample or figuring out what a confidence interval for a sample is, right? So SPSS always uses the t-table. So you got a little bit of a choice on there if you got a really big sample size, and this is a pretty big sample size. But the point of this exercise was not to abbreviate how to do this, but actually do it. So we're actually going to use the actual t-value for a sample size of 100. So let's see, sample size of 100 would mean that our t-score is going to be, and this is for 99% confidence, 95% confidence interval. T is equal to right tail probability. T is equal to 0.025, meaning that in the right tail, you have 2.5%, and you have, since it's symmetrical in the left side, you got 2.5%. So that's 5% chance of being outside, your true mean being outside that range, hence a 95% confidence interval. So I'm going to go down here to 100, and it would be 1.984. So it's plus or minus 1.984 times our standard error. And our standard error is going to be equal to, our standard deviation of our sample divided by the square root of our sample size, which is equal to 30 over 10 is equal to 3. So this is going to be 180 plus or minus 1.984 times 3. So our confidence interval is going to be up. Didn't get my pointer back. Okay, it's going to be 180 plus or minus 1.984 times 3, hence our margin of error is 5.952. I'm going to put that into memory, clear that out. 180 minus our margin of error is equal to 174.04. I'm going to leave that. I'm not going to bother to copy that. I'm just going to show it to you, right? And now the upper limit of our confidence interval is going to be 180 plus, I'll recall this, it's going to be 185.95. Okay, so that would be your confidence interval for a situation where you have a sample size of 100 and this mean and standard deviation for your sample. Okay, so now the next part of this problem asks something a little bit different. I think the next part of this problem changes only one thing, doesn't it? It changes the sample size. So now, what about if your sample size, instead of being 100, if your sample size is 25? What changes if your sample size is 25? Right, the t-value that you're going to use. So you go back to our t-table, and look, just happen to be lucky, and 24 degrees of freedom is a t-value of 2.064. So this is going to be 180 plus or minus 2.064, right? 24 degrees of freedom. Well, there is one other thing that changes, isn't there? The standard error changes, because now it's 30 divided by the square root of our sample size, which is 25, which is 5. So that standard error becomes 6. Right? So not only is our margin of error wider because our sample size is smaller, So our standard error is larger, but it's also because our t-score, the value that we're using for our t-score in 95% confidence interval is larger as well. Okay, so we would calculate that out, and that would be our confidence interval. Now, what about if I now make another change and say I want a 99% confidence interval, sample size of 25? Well, now it's going to be 180 plus or minus. Well, the sample size didn't change, so the standard error is still 6. 30 over the square root of 25, 5 is 6. But now what about the t-score? Well, the t-score for a sample size of 25 or 24 degrees of freedom, instead of being 20.064, is now going to be 2.797. So this is going to be 2.797. So now this gives us our two numbers for our 99% confidence interval when we only know the population standard deviation. Okay, so I'm going to do one more example. Okay, let me get the pointer out of the way here and clear all this out of my calculator. And let's erase this. Okay, a major metropolitan newspaper surveyed did a simple survey, a random sample of 200 voters. They asked whether they had planned on voting for a new bond issue. You know, I'm gonna change this from 200 voters to, it's kind of like a large sample. I'm going to call that, instead of 200 voters, I'm going to call that 50 voters. And I'm going to say that out of those 50 voters, that 55 of them surveyed, said that, 26 of them said that they plan to vote yes. Okay, now, the proportion of people that voted yes, what is the proportion of people that voted yes? Since this is a sample, we don't know what P is, a true population proportion. I hate when it corrects with capital letters. I got to turn that off. I hate that. Okay, the proportion of people that in the population that vote yes in the election is going to be P. That's going to be our value P, the proportion. When we take a sample like this, a survey like this, well, then we refer to the proportion of people that said that they're going to vote affirmatively or that are successes, you know, people that say what we're looking for them to say, right? We're going to call that P cap instead. Just like we used X bar to represent the sample mean, we use P cap to represent the sample proportion, right? So P cap, 26 out of 50, P cap is equal to 52%, 0.52. Okay, that's what P cap is equal to. Okay, so what is a 95% confidence interval for the true population proportion? The true proportion of voters in this population who will vote yes. Well, right now it looks like this proposition is going to pass because over 50% from our little measly little survey of 50 voters. Well, hang on a second here. Just like this is a point estimate. We're estimating what the proportion is, just like we estimate what the mean is. Since they're single numbers that represent the middle of those values, a lot of time we call those point estimates, right? So this point estimate is 52%. But we're not really sure about that. There's a certain amount of variability in here based on what the variability is here. In other words, is it 10% of the population, 90% of the population, and so on and so forth. So we need to do the same thing that we were going to do before when we were working with the means. We're going to do the same thing with the proportions. Okay, what's that going to be? Well, now, instead of X bar plus or minus 1.96 times the standard error for my confidence interval, I'm going to use P cap plus or minus 1.96 times our standard error. Okay, So what do I do now? Well, I have the same issue with how well I know the true. In other words, how do I know what standard error is? Well, the standard error is equal to the square root of P. P is the population proportion times 1 minus P, the 1 minus the population proportion over the sample size. Well, gee, I don't know the population. I got to use P cap in there because that's all I know. So again, I'm dependent on how well my sample really reflects the population proportion, right? So I need to use a t-value here, just as I did with calculating confidence interval for the mean. Okay, so my standard error is going to be equal to the square root of P times 1 minus P over N. So that's going to be equal to the square root of 0.52 times 0.48 over my sample size, which is 50. That's a pretty small sample size for surveys, actually. Okay, is equal to, okay, let's figure out what that is. That is going to be equal to 0.52, whoops, 0.52 times 0.48 equals this, divided by a sample size of 50, equals this, take the square root of that, and we have 0.07. Now I am going to put, that's my that is my margin of error now. Oh, no, wait a second, not my margin of error yet. It's my standard error, right? So my standard error now has to be multiplied by, well, maybe 1.96, maybe not. With proportions, usually we're dealing with sample sizes that are much larger than what we deal with other numerical variables. So we very often will just use 1.96. Yeah, and because sample size might be 1,000 people or 2,000 people or something like that. But with a small sample size like 50, we need to adjust this because we're dealing with a relatively small sample size. Just the same way as we did with the mean. We need to put a t-value in here based on the sample size or degrees of freedom again. Okay, so what's that going to be? Well, this is my standard error. Now I'm going to multiply not by 1.96, but I'm going to go back to my t-table. And my for my degrees, my my t-value for a sample size of 50 would be 49 degrees of freedom. I'm going to, since this table doesn't give it that definitively, I'm just going to use 50, 2.009. I'm going to call it 2.01. Okay, so it's going to be equal to 2.01 times the value that I just calculated. So I'm going to multiply this by 2.01. Okay, and that's 14%, 0.14. Okay, so now what have I got at this stage? What I've got is 0.52 plus or minus our margin of error, which is 0.143. Right? So what is that going to be? That's going to be, I'm going to see if I can't do this by hand. Okay, let's see, what's that going to be? If I subtract it, it's going to be 7, 11, 7, 4, 3, 0.377, and if I add it, it's going to be 0.663. So our 95% confidence interval for the true population proportion is between about 38% and 66%. So we really don't know this all that precisely. Did I get that margin of error correct? Let me just try that again. I just want to check that, because I hate to get emails telling me I did it wrong. Oh, okay. I'm going to do this again. So clear. clear pointer, clear. Okay, so 0.52 times 0.48 equals that, divided by 50 equals this. Take the square root, 0.07. Nah, we did it right. And then what was it again? 2 point, and multiplied by 7% multiplied by 2 is about 14%. Yeah, that was our confidence. That was right. That was our confidence interval for that proportion. So where have we gone today? We've gone from calculating confidence intervals in kind of an artificial fashion for situations where we know the population standard deviation, or proportions when we know we make believe we know the population proportion. And we've improved our understanding of the fact that when we estimate our population standard deviation from the sample standard deviation, we have to make an accommodation for that. And the t-distribution is our accommodation for that. Okay, each individual value, each individual t-distribution, let me just show you a quick look at what that might look like. Where the z distribution, okay, the standard normal distribution looks something like this. And this is where our table comes from. It starts with a mean of 0 and a standard deviation equal to 1. Okay, so that 95% of the population is between 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. Okay, or in fact, since the standard deviation is 1, just that value itself, that's 95% of the population. So now, if we look at the same distribution, a t-distribution, for a sample size of 100, right? Well, that t-distribution, we actually have to be a little further out than 1.96 in order to have 95% of the population between these two values. So that might be something like 2.1 instead of 1.96. So what does our t-distribution look like? It's a bit wider than our standard normal distribution. Well, what about if the sample size is equal to 25? If the sample size is equal to 25, it looks even wider, right? Hence, our critical values for what our 95% of the possibilities are is a number that's larger than 1.96 and progressively larger as the sample size gets smaller. Okay, and that's why we wind up with t-values getting bigger and bigger and bigger as the sample size goes down. So I'm going to post an assignment that introduces some problems like this. Won't be very complicated, but what this means is next week we can start to talk about applying this. Okay, and by applying this, I mean taking it in situations like where, for instance, let's say we want to compare two populations. We want to know whether population A has a higher blood pressure, average blood pressure, than population B. Okay, well, how are we going to compare the two of them? Well, what would we do if we were doing a study? We would take a sample from population A, and we would take a sample from population B. I'm showing it as equal sample sizes. They may not be equal sample sizes, but we can determine that, right? So sample from population B, it's advantage of population B. We then calculate a mean for population A. Say the blood pressure comes out to be 92. And we calculate a mean for population B. Let's say it comes out to be 96. And we say to ourselves, can we say that the blood pressure for population A is different than the blood pressure for population B. Is this enough evidence to say that? Well, the problem here is that, if I took a sample from population A of 100 people, first time I take it may come out to be 92. Second might be 94. Third might be 89. Fourth might be 97, right? It's not going to come out the same number every time I take a sample. Okay, so now we have to figure out what's the probability that these two are far enough apart that there's less than a 5% chance that they came from the same population, that the population they came from has the two populations have the same means. How likely is that? Well, one of the ways we might be able to do that is let's say sample size was 25. Sample size here was 25. We might be able to see, and using the t-score, we might be able to say to ourselves, okay, standard deviation of this was 10. Standard deviation of this one was 8. Using our t-score, we might be able to say, well, I'll calculate a confidence interval for A. And maybe it came up 88 to 93. And I'm going to calculate a confidence interval for 96. Maybe it came up 94 to 98, right? So I'm 95% certain that the true mean for A is between 88 and 93, and I'm 95% certain that the true mean for population B is between 94 and 98. Well, these two don't overlap. If I'm 95% sure that the true mean for population A is between these two numbers, the true mean for population B is between these two numbers, can I also say I'm 95% sure that the two means are not equal? The mean for population A does not equal the mean for population B with 95% certainty. Does that sound reasonable to you? Right? Sounds reasonable, right? So if these numbers had been 88 and 95 versus 92 and 98, well, now they overlap, don't they? So it could be that maybe they have the same means, these two populations, in reality. So I can't be 95% sure that they're different. So I want you to erase this from your mind because we don't use confidence intervals this way, right? What I just told you is a big lie. Don't tell anyone that I showed you that. You kind of, if you're kind of, when you get kind of an introduction to confidence intervals, it's very tempting to use the confidence intervals that way to see if they overlap or not. You really shouldn't use them that way. We have a special tool for testing this, testing these two means. It's really almost the same as looking for the overlapping confidence intervals, but it's really a bit different in the way that it works. And that difference is very important. I just want to introduce this now. And that difference is that instead of looking for overlapping confidence intervals, what we're looking for is we're going to look for the difference in the mean between population A and population B, right? We're going to look for the difference. And we're going to try and determine, based on the variability of A and the variability of B, we're going to try and figure out whether or not the difference between these two is if we can say with 95% certainty that we can reject the idea that the difference between these two is 0, that they're far enough apart that we're sure that the difference is really there and it's not 0. So we're gonna apply this idea kind of based on the confidence intervals, right? The way the confidence intervals are calculated. We're gonna apply this idea using something called a student's t-test. Okay, and the student's t-test is specifically designed to compare the means of two populations in terms of samples, right? Compare the means of samples, but in reality, that's a substitute for comparing the means of the populations. That's called student's t-test. Student is the pseudonym for the guy who invented the test, developed the test. It's not actually done by students. It's not, that's his name or his pseudonym, right? So we're going to learn about that t-test. He was a chemist in a brewery, and he used it to determine when they did small batches and they had to test them. They didn't have a lot of data. They didn't have a lot of data. Sample sizes were small, so he needed a tool that would give him a reliable way of estimating how certain he could be that two samples two groups were different from one another. In other words, if he altered something in the process of making the beer. Unfortunately, the school won't let me bring in beer so we can test it for ourselves. So we'll just have to work with the numbers next week. Okay, so I think now's a good time to call it a night. Now, the thing is though, go through that video too, play that video. It's gonna be a little advanced, right? But don't let that scare you away. Just absorb as much of it as you can, because I'll break it down into some simpler ways of looking at it next week. Okay, so for you guys that are online, that are still with me, good afternoon. And for you, thank you for coming in.